welcome back. We left our last video on a cliffhanger. We took these two data sets, A and B. We calculated the mean and median for both data sets. And what we noticed was the medians are exactly the same, but the means are vastly different. So let's analyze this a little further, find out what's going on here. The medians are the same, but the medians are different. What is the driving reason behind the difference in the two means? I mean, it has to be this number, right? That's the only difference between data sets A and B. It's this number right here. So what we see is this very high number, this outlying value, is very much affecting the mean, but it doesn't affect the median at all. So what we can say is, conceptually, if you can think of like some kind of graphical display for these data sets, like a histogram or something, this number right here, if we were to make a histogram, this number would be way out here, where the rest of the data would be over there. 11,976 is way over here. This number, all by itself, is pulling the mean from 8 all the way up here. This number is pulling the mean towards it. So the mean is very susceptible to outlying values. Whereas the median, solid as a rock. Doesn't matter. The median will stay where it is, even if there are crazy outliers on the ends. Because the median only takes into account what's in the middle of the data set. So, the mean is affected by outliers. The mean is affected by outliers, but the median isn't. The mean is susceptible to being changed by outliers, and the median is going to stay where it is. There's a name for this property. So we call the median robust or resistant. Right? Both of these terms mean the same thing. Depending on the statistician you ask, they might use one word or the other. But if we call a statistic robust or resistant to outliers, it means that it is not affected. Right? We can mess with either end of a data set. The mean's just going to go back and forth like a yo-yo because these really large values are going to affect that mean. But the median is robust. It's resistant. It's like a big old Snorlax just sitting right in the middle of the data set. Sorry for those of you who don't know Pokemon. Right? Snorlax is a big old guy who just sits on the ground. Right? Okay, so this is a positive characteristic. We're going to come across data sets that have outlier values on the high or low ends. And we would like to have a statistic that performs well under those circumstances. Because let's be honest, the mean of data set A is 8. That's a pretty good measure of center for this data set, right? I mean, yeah. Is 1,337 a good measure of the center of this data set? Not even close, right? 1,337 is way higher than almost every value here. So for data sets like B, the median is going to be what we want to use as our measure of center. So, well, why don't we always just use the median then? Well, before we can answer that question, let's get something straight. If a data set has outliers and or is skewed one way or the other. Okay, so it doesn't necessarily have to have outliers for the median to be good. If the data set is skewed, we also have this type of issue. Right? The mean gets pulled towards the direction of the skew, which we don't want because that takes it away from the center. So if a data set features one or both of these characteristics, we want to use the median. As the measure of center. Right? If you've got a data set like B and you try and use the mean as the measure of center, it's not a good measure of center. You should use the median in those cases. Right? Now, let's go back to our question. Why wouldn't we always use the median? Right? For data set A, the mean is 8, the median is 9, they're both pretty good. Why can't we just use the median there? Let's go back to how these statistics are constructed. For the median, we're only using the middle value or the middle two values. Those are the only numbers that count. And while that provides a robust or resistant characteristic, because we're only using those values, typically when we calculate statistics, we want to use as many values as possible so that that statistic is a measure of the entire data set and not just those values in the middle. So if we have a nice, neat data set here, the median's only using the middle value or the middle two values. For the mean, all of these numbers are included in that calculation. We're using all of them. Everyone's included. It's fantastic. It's like that kid in grade school who doesn't just invite his friends to the party, but invites everyone. Isn't that great? Go to the party where everyone's invited. That's so nice, right? If a data set is nice, and by nice I mean it doesn't have these things going on, then we want to use the mean because it's more inclusive. It uses all the values of the data set. So, if the data set is, I don't want to say unimodal necessarily, it doesn't have to be unimodal. The number of peaks doesn't really matter in this case. It's all about whether it's skewed or symmetric. Okay, so if your data set is symmetric and has no outliers, then you use the mean. Okay. Now, you could memorize this and try and connect it that way, or you can understand why this is the case. If your data set has outliers and or skewness, we want to use the median as a measure of center because it's robust. It's not going to be pulled towards the direction of the skew or the outliers. If the data set's symmetric and has no outliers, we want to use the mean because it uses all values. And in general, that's preferable to something that only uses one or two. So, now that we know this, if we were to be given a data set or a histogram or something like that, we would be able to tell by the way it looks, by its shape, whether it has outliers or not, we would be able to determine which of these measures we should use. If it's skewed or has outliers or both, we want to use the median for center. If it's nice and symmetric and has no outliers, we'll use the mean. Okay, so we're already in a better place than we were in the last video when we were like, the center's about here. Now we know how to calculate the mean and median as long as we have the raw data values. And we know when to use which one as the measure of center. All right. So, there are more statistics that we can calculate. Not necessarily as measures of center, but statistics that could be helpful in describing a data set, like one of these. So, let's take data set A. We'll just analyze it for now. Let's just take data set A. One, 3, 3, 6, 9, 10, 11, 14, 15. Now we've already established that the median of data set A is 9. Right? And that's because there are 9 values here, and we use n plus 1 over 2. That's 10 over 2, which is 5. It's the 5th value. The median is 9. And that's great. So let's cut this data set in half. And since there were an odd number of values, I circled the middle one. Let's exclude that and use each of the numbers that are left and split the data set in half. So we're going to separate the lower half from the upper half. We're in the process of calculating some additional statistics that will help us describe the data set. Okay. So now we've got 2 halves of the data, and since there was a middle number here, we left it out. If this data set had an even number of values, then we could split it in half exactly, right? And there would be the same number of values on each side. But since it's odd, we have to get rid of the middle number. Right. Now, let's take the median of the lower half. So we're just taking the median of these 4 numbers. So how do we do that again? You might know what the median of the lower half is, but just to go through the process again, there are 4 values here. So we take that plus 1 over 2 equals 5 over 2 equals 2.5th value. So that means to take the average of the second and third, since they're both 3, this is 3. The median of the lower half is 3. And the median of the lower half, that's too many words to describe a statistic. So we're going to call this number Q1. Q1 equals 3. And we'll talk about what that means in just a sec, but I want to do the same thing for the other half. Same thing for the other half. So let's take the median of the upper half. Again, there are 4 values here, so it'll be the 2.5th value again. And that's going to be the average of 11 and 14. So that's 25 over 2. It's 12 and a half. 12.5. We're going to call this, any guesses? People who took the 1 semester class may already know this. That's right, we're going to call it Q3. Q3. What happened to Q2? I don't know. Actually, we'll talk about that in just a sec. So the median of the lower half is Q1. The median of the upper half is Q3. So we are building up to being able to describe a data set like data set A in an additional way. So let's see here. We now have the median of the entire data set, which was 9, and then we took the median of each half, Q1 and Q3. So we could calculate those 3 statistics for any data set. And if we were to do that, say for any data set, you've got the minimum value down here. This is kind of like a number line. Not really, though. This is the maximum value. The value right in the middle, or the average of the middle 2, is the median. So we're saying there's 50% of data on either side of the median. But then we took just this half and cut it in half. So the number right in the middle of those 2 is Q1. And that splits this into 25% each. This is 25% of the data values. 25% of the values in the data set are between the minimum and Q1. 25% of the values in the data set are between Q1 and the median. Q3 does the same thing on this end. So, what these Q1 and Q3 values help do is to take any data set, and as long as you know these 5 values, the minimum, Q1, the median, Q3, and the maximum, you can split a data set into quarters. And in fact, Q1 is called the first quartile. Quartile means split into quarters, right? So when you split into quarters, the first quartile of values is between the minimum and Q1. Q3 is the third quartile. So what happened to Q2? It's the median, right? We just never call it Q2. We just never call it Q2 because it's more special than that. It's the median. It is the absolute middle of a data set. So, with these 5 values, we can split a data set into quarters, and that's going to be useful to create additional displays for a data set, which we'll see probably in another video or two. And it leads us into this idea, which is instead of splitting the data set into quarters, what if I wanted to split a data set this way, where 43% of the values were less than whatever this number is, and 57% of the data values were greater than that? Okay. Obviously, we can't use any of the quartiles for this number, but there is a statistic that allows us to split a data set into really any percentages. We would call this number in particular, since this is 43, it's a percentile, right? So specifically, the 43rd percentile is the value of a data set at which 43% of the data is less than it, right? So you can take any percentile of a data set, to split it into whatever distribution you want. If you want 95% of the data to be less than a value, that's the 95th percentile. A common usage for percentiles is standardized test scores. So if you took ISTEP or the SAT or something like that, most of the time they report your score as a percentile because the score itself isn't really all that important. It's kind of arbitrary how the test is scored. The percentile tells you how many percent of students scored less than or equal to your score. So if you scored in the 90th percentile on the SAT, it means you did better than or the same as 90% of students on that test. Only 10% of students did better than you. So it's a great way, percentiles, to show you what value is the point where such a percent is less than that or greater than that. Okay? So quartiles split the data into quarters. Percentiles split the data into percentages. For percentiles, all you need to know is this concept. You don't need to know how to calculate these. First of all, it can be quite difficult. The quartiles, you do need to know how to calculate, and this is how you do it, right? Find the median first, then split the data in half, find the median of each half. You can do it that way. And I do want to add, before we move on any further, a percentile, if it's like a test score, the 43rd percentile does not mean that you scored a 43% on the test. or that you got 43% of the points. It doesn't mean anything like that. The percentile only tells you where that value is in relation to the other values. It means 43% of the data values, the people who took the test, did worse, got a worse score, or the same score. Okay, don't confuse the percentile with the actual score on the test, for instance. That's not what it means. All right, so we've learned quite a bit here. We know how to calculate the center of a data set, whether it's the mean or median, and we know when to use which one. That's going to be really helpful. So let's clear this all up a little bit and talk about something new. Okay, so I said we'd get to something new, but I do want to start with two new data sets, but I want you to think about what the mean and median are for both data sets. Go ahead and calculate those real quick. Pause the video. Come back when you're ready. Did you come up with these? They're all 50. The mean and median of both data sets is 50. So let's pretend that the only way we knew how to describe a distribution was describing its center. It doesn't matter which measure of center we use, it appears these data sets are exactly the same. But clearly they're not the same, right? How would you describe the difference between these data sets? One's more spread out than the other, right? So that's why when we're describing a distribution, we do want to describe its center, but we also want to give some attention to how spread out the data set is. Because it's important whether it's relatively compact or whether it's more spread out. That is something we want to talk about. So let's discuss a few different measures of spread that we can calculate for a data set and how good or not so good each one is. The first measure of spread I'd like to talk about briefly is the range. Right? You should know how to calculate the range. I believe you've seen that before in at least one class, if not several. Right? It's the largest value of a data set minus the smallest value. I will say that there are students that do make a mistake in calculating the range in that they just report that the range for data set C, for example, is 30 to 70. They just report the minimum and maximum values. It's possible that back in the day that's how the range was defined. In this course, the range is the difference between those values. So the range will be a single value. That's what we want here. So for example, the range of data set C would be 40. The range of data set D would be 400. So I actually put in my notes here, in terms of measures of spread, the range is kind of poopy because it doesn't really say a whole lot. It's kind of like the median in that it only uses two values of the entire data set, which when there are 5 isn't that bad. But think of a data set that has 100 values. You're only using 2 of them. And on top of that, they're the 2 most extreme values. So if you've got outliers on either end, that's really going to affect the range, and that doesn't really give you a good idea of how spread out the data set as a whole is. We want to be able to use more values than just these. Okay? And we definitely don't want to use the endpoints because outliers can really screw that up. So we can probably do better than that. So let's try and find a more robust or resistant measurement of spread that doesn't use the extreme values of the data set, but that uses values closer to the middle. So I think it might be important let's see if we can use what you just learned earlier in the video. If this is the minimum value, and this is the maximum value, if we just took the difference between these, we'd have the range. And we said that's not a very good measure of spread. What I want to do is separate the data set into these percentages. And I want to know what values go here and here that would allow me to see how spread out the middle 50% of the data set is. Not the whole thing, but the middle 50%. So what two values am I going to use here to separate the data set in this way? If you said Q1 and Q3, congratulations, that's correct. We could use the 25th and 75th percentiles. Those are nicknames for Q1 and Q3. That's what they are. They're percentiles as well. But since they're special percentiles, they get special names. Right? So Q1 and Q3, instead of taking the difference between the largest and smallest, or the maximum minus the minimum, we can take Q3 minus Q1. And it's going to be Q3 minus Q1 and not Q1 minus Q3, because remember, Q3 is always going to be bigger than Q1. We want this difference to be positive. This difference is called IQR. And IQR stands for interquartile range. But since interquartile range involves a really long word, and us statisticians, we prefer to work with numbers, but words sometimes get in the way, we just use the acronym IQR. Right? Interquartile range, IQR. It's Q3 minus Q1. And yes, we're still just using, I suppose you could say that's two values here. But remember how many values we used in order to calculate Q1 and Q3? It was more than just two. And we're not using the most extreme values. We're using values that take up the middle 50% of data. So it's better than the range. And it's resistant to outliers and skewness because these values aren't really that close to the ends of the data set. So that's really helpful. So I actually want to stop here. There is another measure of spread that we use, and it uses all the values of the data set, kind of like the mean did for the measure of center. And we'll talk about that in the next video. But for now, have a great day, and we'll see you in the next one.